Hey guys, in this video we are going to be finishing up our mole unit. We're going to be looking at empirical formulas and molecular formulas today. And all of this is going to be based off of percent composition to begin with. So we're going to use percent composition of a compound to find the empirical formula. Empirical formulas are formulas showing the lowest whole number ratio of atoms in a compound. So all of our subscripts should not be divisible by one another. It should be in that lowest whole number ratio. There's a little poem for remembering the steps of empirical formulas, and then we're going to actually practice calculating these. So the poem is percent to mass, mass to mole, divide by small, and then multiply till whole. So this is going to be a 4-step process for each one of our problems. So make note of percent to mass, mass to mole, divide by small, multiply till whole. And I'll write that with our next example as we go through how to actually calculate these. So here's a problem that we can come across. So we have a compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. And we want to know the empirical formula of the compound. So I'm going to write our steps to our poem across to the side. So we had percent to mass, mass to mole, divide by small, and then multiply till whole. So those are our 4 steps that we're going to take. And similar to percent composition, where we had to do the problem for each substance, unless it's specified otherwise. For empirical formulas, we're going to have to do these 4 steps for every substance in our compound. So our compound here contained nitrogen and oxygen. So we're going to have 2 problems. And it is easiest to work through the problems together because you're doing the same steps. So for our first step, we have percent to mass. This one, you simply take the percentage as written, and that becomes the mass of your substance. So you just change the percent sign to grams. So for 25.9% nitrogen, we're going to make that 25.9 grams of nitrogen. We had 74.1% oxygen. We're going to make that 74.1 grams of oxygen. So that's your entire first step. Just change the percent sign to grams. Our second step is mass to mole. So whenever we do conversions going from mass to mole, we have to use our molar mass. So this is going to be a 1-step mole conversion for both of these. Since we have grams and we're trying to get to mole, remember to cancel out grams, it will go on the bottom of our next step to get into mole. And that's going to be the same for both substances. So remember, grams per mole is the molar mass off the periodic table. So for nitrogen, it's 14.01 grams per 1 mole. Oxygen, it's 16 grams per 1 mole. And note here, oxygen is not diatomic because it is in a compound. So we're going to calculate moles for both of these. So 25.9 divided by 14.01. And don't round these. You want to keep several decimal places because we're still going to be using them in future steps. So for nitrogen, that's 1.849 moles. For oxygen, 74.1 divided by 16 is 4.631 moles. That was the second step, grams to mole for both substances. The third step is divide by small. So you have moles for both nitrogen and oxygen. Whichever number is the smallest, you are going to divide everything by that number. So the smallest is the 1.849. So we're going to divide everything by 1.849. So 1.849 divided by itself will equal 1. 4.631 divided by 1.849 is going to be 2.5. And then our last step, multiply till whole. These numbers are going to be our subscripts in our formula, and we cannot have a decimal number as a subscript. So if these are already whole numbers, you don't have to do this last step. But in this case, 2.5 is not a whole number. So we need to figure out what to multiply everything by so that 2.5 can be a whole number. And whenever you have to multiply, it's not going to be very difficult numbers. It will be numbers like 0.25, 0.5, 0.75, 0.3, 0.6. So things that you can generally multiply by 2, 3, or 4 to make it a whole number. In this case, because we have 0.5, if we multiply by 2, it will end up being a whole number. But if we multiply one substance by 2, we have to multiply everything by 2. So 1 times 2 is going to equal 2. 2.5 times 2 is going to equal 5. And these numbers now, since they're whole, are going to represent the subscripts in our formula. So our empirical formula is nitrogen with a subscript of 2 and oxygen with a subscript of 5. Let's look at another problem. Here was the let me see if I have another one. Yes. Let's look at this one. It has 3 substances, but we can treat it the same. What is the empirical formula of a compound containing 67.6% mercury, 10.8% sulfur, and 21.6% oxygen? So we're going to treat it in the same way and go through the exact same steps. So percent to mass, mass to mole, divide by small, and then multiply till whole. So here we have 3 substances, so we're going to have 3 different problems. We're going to have mercury, sulfur, and oxygen. So yet again, percent to mass. For mercury, 67.6% is going to be 67.6 grams of mercury. For sulfur, 10.8% is going to become 10.8 grams. And for oxygen, 21.6% will become 21.6 grams. Our second step, grams to mole, remember it's going to be our one-step conversion. And since we're starting with grams, to get rid of grams and change to moles, grams will be on the bottom of our next factor. And you have to look up the molar masses off your periodic table. So for mercury, or hydrogen instead of mercury, mercury's molar mass is 200.59. And that's per 1 mole. Sulfur's molar mass is 32.07 grams per mole, and oxygen is 16 grams per mole. So we can go ahead and solve for moles of all three substances. For mercury, 67.6 divided by 200.59. And remember, don't round off too early. Keep several decimal places. So that's 0.337 moles. For sulfur, 10.8 divided by 32.07 is 0.337 moles. And for oxygen, 21.6 divided by 16 is 1.35 moles. Our third step is divide by small. So the smallest number of anything is the 0.337. So we're going to divide everything by the 0.337. So for mercury and sulfur, 0.337 divided by itself is equal to 1. For oxygen, 1.35 divided by 0.337 is equal to 4.00, so 4 exactly. Since everything is a whole number, we do not have to do that last step and multiply till whole. So our empirical formula, remember these numbers are our subscripts. So our empirical formula is mercury with a subscript of 1, sulfur with a subscript of 1, and oxygen with a subscript of 4. Let's move on to molecular formulas. These are going to be a little bit easier. So the molecular formula of a compound, it can be the same as the empirical formula. That is possible. Or it can be a whole number multiple of the empirical formula. So these do not have to be reduced like empirical formulas need to be. So to find molecular formulas, you're going to take the known mass of the compound, so the molar mass, divide it by the mass of the empirical formula, so by the empirical mass, and that is going to give you a whole number, which is the ratio of the molecular formula to the empirical formula. So if you're given a whole number that is not 1, that whole number will multiply by all of the subscripts in the empirical formula to give you your molecular formula. So let's look at how one of these problems will look. Here we have an empirical formula for hydrogen peroxide that is HO. The empirical formula's mass is 17.0 grams per mole, and the molar mass of hydrogen peroxide is going to be 34.0 grams per mole. What's the molecular formula for hydrogen peroxide? So our setup, we had our molar mass, which it tells us is 34. So always the larger numbers should go on top here. That is divided by our empirical formula's mass, which we said was 17. If we divide those, we get that these are at a ratio of 2. So that means that our molecular formula, the subscripts are 2 times the subscripts in our empirical formula. So if we multiply this by the subscripts in HO, so you can easily just distribute it, our molecular formula for hydrogen peroxide is H2O2. And that's our molecular formula. Let's look at another sample with these. Here we want to calculate the molecular formula of a compound whose molar mass is 60 grams per mole, and the empirical formula is CH4N. So here we were not given both masses, but we were given the empirical formula. So we can set this up the same. We have our molar mass on top. the 60 grams per mole. It did not give us the empirical mass, but we can find that just like we would molar mass. So for CH4N, carbon is 12.01. We have 4 hydrogens. Hydrogen is 1.008. And add to that nitrogen that is 14.01. And if you put that in the calculator, you get 12.001 plus the 4 times 1.008 plus 14.01 is a molar mass for the empirical formula of 30.052. So if we divide those, remember you should end up with a whole number. So the calculator tells you it's 1.996, so that would round up to 2. And remember, that is the number that we multiply by all of our subscripts in our empirical formula, so you can easily just distribute it across. So that means that our molecular formula, carbon, will now have a subscript of 2. Hydrogen will now have a subscript of 8. And nitrogen will now have a subscript of 2. And remember, this does not have to be reduced. So that will be our molecular formula. Let's look at one more, just for good measure. Find the molecular formula of ethylene glycol, which is used as antifreeze. The molar mass is 62 grams per mole, and the empirical formula is CH3O. So our molar mass is the 62 grams per mole. Our empirical formula, it did not give us the mass, but we have the formula so we can find it. Carbon is 12.01. Add to that 3 hydrogens that are 1.008 apiece, and add to that oxygen, which is 16. So when we multiply and add that together, we get a molar mass of 31.034, which yet again is equal to 2. So we can multiply that by all of the subscripts in our empirical formula, and our molecular formula will be C2H6O2. And on a side note, it is possible for the molecular formula and empirical formula to be the same if when you divide them, you get that that ratio is 1. Make sure you're practicing these skills and then use them to answer the mole check-in.